In previous videos, we talked about the components for designing a neural network, the choices that you need to make about the type of network, the size of your data set, what proportion you're going to train, and the number of inputs and outputs and hidden layers. We look at the number of repetitions during training that we call epochs, and we choose activation functions. And we talked about in a previous video the different choices when it came to those activation functions. What we're going to do in this video is create a multi-layer perceptron neural network. And so this is the simplest form of neural network. It's often called a vanilla neural network. It is a forward neural network. So if we just go back to videos or to slides we had before, we talked about feed forward. So this is a feed forward method where we're going to go one way through the neural network. And we're going to have back propagation, which is once we have gone through the network and then assess the output for accuracy or minimum error. Then what we do is we tune the model, change the hyperparameters, and then we go back through again. That's called back propagation. So let's do that with our vanilla neural network. And we're going to need to make some choices here. There are different methods for optimizing the model. If one isn't working particularly well, we can try different ones. We'll look primarily here at ATOM, but there's also SGD and RMS prop. And then we choose a model loss function for how we are going to measure the error. If it is interval or ratio, we're going to use mean square error. If it is a binary classification, so it's either true or false, we'll look at the binary cross entropy to measure that error. And if there are multiple variables we're classifying, we'll do the categorical cross entropy. In terms of our metrics, we'll use the same metrics we use for classification models and regression models. So we can use MAPE and MSE and R squared for like we did with forecasting and regression. And we can use accuracy. We can look at precision, recall for the binary classification models like we did when we did classification. So we're going to create this multi-layer perceptron. We're going to have our input is going to be multiple variables like we do with multiple variable regression. We're assuming fully connected neurons, and we need to choose a nonlinear activation function, have at least 3 layers. So let's dive in. All right, we are going to use the Penguins dataset that we've used in the past. You can get that Penguin dataset from Google Cloud, or you can just install it directly using pip install Penguins. Oh, too many things running. Let me just close something else. Oh, I don't think I did it. Let's try it again. Manage sessions, terminate other sessions. Okay. Running too many code in Google Colab. Google Colab isn't really built for a lot of high level, lots of computing power. You're running it in the cloud. It's free. So you're limited. So if you're starting to do this with large sets of data, and we'll look at some examples of that where you might be building neural networks with even bigger data, lots of images, for example, you might want to leave, you might have grown out of Google Colab and want to move on to running Python on your own computer and say like Microsoft Visual Studio. All right, so from Palmer Penguins, we're going to import and load our penguins. Our data sets are on the smaller side, even though we've been talking about approaches for bigger data. We're actually been applying it to smaller data. Okay, install and then load her up. All right, so we've loaded in our data and now we can look at it itself. So you'll recall there is the column for the 3 different species of penguins. We have bill length, bill depth, flipper length, and body mass, as well as gender and or sex and year. And so what we're going to do is first we're going to do some one-hot encoding. So we're going to take this column here that is the species, and we are going to create a variable that is simply identifying if we have an Adelie penguin or not. So we're going to create a new column from our original. So the original column was a deli. We're creating a new one, or sorry, we're creating a new one called a deli from the original that is species. And we're going to then replace, if it says a deli, we're going to make it say 1. If it says Gen 2, we're going to make it say 0 and chin strap 0. And we're going to do that in place here. Then what we're going to do, because when we're dealing with these neural networks, and particularly ones that are classification regression type models that can't deal with missing information, we can't predict the type of penguin using flipper length if no flipper length is provided. So we are going to drop the NAs, the missing information. At a later time, we'll have a video about imputing data. What if you can't drop? Then how do you deal with that in your neural network? We'll have a future video on that. All right, so we're going to need a number of different packages. Now, sklearn has a built-in MLP classifier and a MLP regressor, and we're not going to do that here because those are very similar and kind of black box to their classification and regression by themselves. What we want to do is get used to using TensorFlow and Keras. And that's what you use for neural networks, where you specify every layer and how that layer works. So we're going to do our MLP neural networks with TensorFlow, even though there are kind of built-in automated processes for these more simplified neural networks. So you're going to need, though, from sklearn model selection, you're going to need that train test split so we can divide our data. We're going to need to standardize our data. So that measurements we have here, bill length, bill depth, flipper length, body mass, we're going to have to standardize those. So make the mean 0. Okay. And neural networks are very dependent on that standardization. They get highly impacted by non-standardized data. So any interval ratio data for a neural network needs to be standardized. So we're going to use standard scalar to do that. We are doing a feed forward model. So that is sequential here in tensor.keras.models. We're using a sequential model. And then, as we said before, there are 3 different types of optimizers: Atom, SGD, and RMS prop. And so you can choose different ones. We're going to use Atom in this particular example here. And then you're going to need some layers. So we're going to have our keras.layers, and we're going to import dense. And then numpy as NP so we can manipulate our data. So install our packages. The next thing we're going to do is we are going to split between our test and training data. We are going to use bill length and bill depth in this model to predict the type of penguin, so a deli or not a deli. And we're going to do our 80-20. So our training data is 80%, testing data is 20%. We're predicting the Adeli one here. We're going to stratify across the Adeli to make sure that there are Adelis in both the testing and training. One of the strange things about this data set is the way that it is actually already sorted is that it's all the Adeli penguins first, then the next type, then the next type. And so the risk, of course, even though you're stratifying, is that based on the way the data is set, you can end up with a lot of Adeli penguins in the training and very few Adeli penguins in the test. And so that can impact your accuracy in terms of false positives and false negatives. So we're adding a statement here to do shuffle equals true so that it is more equally split. The stratify is just making sure there is some in each, but we want to make sure that it's more equal in each. So let's do that shuffle. We didn't do the shuffle, I think, in the regression model, and so that could be impacting that model as well. In terms of that big difference we had between the test and the train accuracy. So realizing after we made that video that the data is really set to just be all Adeli penguins. So if you're going back and doing that one, shuffle it, and that will actually change that disparity between the accuracy of the training versus accuracy of the test. All right, so we're going to standardize. So we do this method we talked about when we did our classification models. So standard scalar, scalar.fit transform. Then we're going to transform both the X-train and the X-test data are standardized. We then call our model here. The model we're using is sequential. We are doing that feed forward that we talked about. Just go back in our slides here. Okay. So we're moving forward one direction through our data. And in Keras, that is called sequential. Now we need to add the layers. So if we're looking at these hidden layers, we have to specify what these layers are in our data set. Now, when you are creating layers, like we talked about in our previous videos, you have layers that live here in the middle, and then you have layers to help convert whatever you've done to your final output. And when we talked about different activation methods, find the slide related to that. There are specific activation methods for converting that final output, and then there's ones that we use more often inside the hidden layers in the middle. So this rectified linear unit is going to be used. It's a hybrid of a binary and a linear function, and we'll use that in the middle. And then because we have a binary classification model, then we'll use the sigmoidal function. I know that's really hard to see. That's tiny here. Here you go. A ReLU for the inside and a sigmoidal function for the outside. Okay. We are also going to have to choose our metrics. And because this is a binary classification, we can use accuracy, precision, recall, area under the curve. Those are all available to us with this particular method. Okay. Let us go in. So model sequential gets us started. And we are going to then do our first conversion is the input into the first layer. So we need to specify the dimensions of the input. It needs to match here the number of variables that you have. So if you have 4 variables, then input dimension is 4. We have 2 variables, the input dimension is 2. We're going to use ReLU. And then when you are choosing here, the number that goes in here, then they're going to be powers of the number of variables that you have here. So we have 2, so that means that you can use 2, 4, 6, or 2, right? 4, 6, 8. No. Oh my God. 2, 8. Trying 2 to the 2 is 4, 2 to the 3 is 8, right? So you're looking at as you go up. So what we're going to do here is we're going to start a very generic starting point for a MLP classification model is 32 and then 16 for your layers. We'll notice when we do our classification and regression that these layers, the number here is going to go down. When we're doing images, we're going to actually make those numbers here go up. Right, so our numbers 32, 16, that's the dimensionality of our space here. So as we're getting closer to a classification, we'll make that number go down. So we'll make this big to start with. So 32 is kind of a general starting point. Our dimensions, we have 2 variables. Our activation function is ReLU. Then we're going to create a second hidden layer. And so notice that the space, we're simplifying the space. And with another activation function here, ReLU. And then finally, we want to convert this to output. So we are going to convert it down to our 1. And then we're going to use sigmoid there to turn it into essentially a percentage or likelihood that this is an Adelie penguin or not. So we have 3 hidden layers here. The space is getting smaller as we go down. So we're going to add in our layers. And now we're going to compile the data here. We're going to use that Atom optimizer. Again, you can use SGD or RMS prop when you are doing that. So you can choose, you can play with them if one is not performing as well as the other. The idea with the optimizers is that we are trying to do our gradient descent, and we're trying not to get stuck in these little local minimums. We're trying to get to the global minimum. And so different ones might perform better or worse for your particular data set. All right, so let's compile our model. Our loss is binary cross entropy because we have a binary classifier, and our metric here is going to be accuracy. So now we have to make a decision as to how many epochs. So with back propagation, what we're doing is we're going through the model, and then we are going to learn from that accuracy, how well it worked. And then we're going to run through it again, having adjusted some of the hyperparameters, and then keep going through. So the epoch is the number of times you're going fully through the system. The higher the epoch, the more that accuracy theoretically should improve as it adjusts all of those weights and bias in our process. We're going to do 200 because, of course, the more epochs, the more time it takes and the computing power it takes. And of course, we talked about before, Google Colab is really just kind of for learning and for basic practice. Once you have the basics here, once you outgrow us and our videos, then you can go and do it outside of Google Colab with much bigger data sets, with much more epochs in terms of tuning. And of course, the data sets we're using here aren't overly complicated. So what we can see as we go through these epochs is you can see each time it's going through, it's measuring the loss. That is our measurement error here. And in this case, we are looking at it in terms of binary cross entropy, as opposed to like mean squared error we would do if it was interval or ratio. And then we can see the accuracy. So we have a pretty accurate model. Once this has run, we can then evaluate the model by having it find the overall accuracy for our training data. And we expect this to be quite high because this is what it was built on. And we see here 99%. What is key is the accuracy of the test data because it was not used to build the model. And can we accurately have it predict here? And so here we are at 97%. All right, what do we do with this? Well, now that we have this model that can identify Adelie penguins, what we want to be able to do is add additional data. So instead of putting our X test in here, you could add an additional data about whatever variables we started with, which were, I think, the two that were bill related. Bill length and bill depth. You could have new bill lengths, new bill depths, pour them in, and this model is now built to identify Adelie penguin or not. Now, in terms of thoroughly analyzing how well this model works, let's create some of the assessments we're used to with our classification model. So we're going to convert what it has predicted, because when you actually look at its predictions, I'm just going to have you show you here what this looks like. So if we do ypred, what you get, well, of course, you have to run ypred. So if I say, okay, predict the actual labels based on my test data, then what it actually outputs is a percentage, a probability that it is an Adelie penguin, not the label itself. So we have to take this information and convert it into a label. And so what we're going to do then is we're going to create a loop here where it's going to populate an empty list called labels. And for I in the ypred, so as it goes through this list here, if the probability is less than 0.5, we're going to say not an Adelie penguin. And otherwise, it's going to be a label of 1 for it is an Adelie penguin. And so we're going to add that to this labels list. That way we can get the classifications we're used to, which is 1 for Adelie, 0 for not. Okay. From our sklearn.metrics, we can do our confusion matrix and have it displayed. We're importing Seaborn as SNS so that we can see this. And we are then going to have it create a confusion matrix from our Y test data and from the labels that have come from our neural network here. And then we can plot this. And what we see here is that in the test data, we have one where we predicted it was an Adelie penguin and it was not, so 1 false positive, and then one where we predicted it was not an Adelie penguin, but it was, so 1 false negative. So you can see why the accuracy was so high. Remember here it is 97% for our test data, because really there was only 2 that were misclassified, 1 of each, 1 false negative, 1 false positive. We could have it output recall and precision from this using those same methods we talked about in previous classification regression type models, our logistic regression, and then our classification. You can do the same thing. Okay. Now, I encourage you to try this with the iris dataset. We've talked about the iris dataset in previous workbooks, and I believe at the end of the classification workbook, it shows you how to pull it. You can also pull it from Google Colab. So grab the iris dataset and see if you can perform this. Create a multi-layer perceptron classification model.